Hello, and welcome to the second part of the chapter on variation formulation of finite elements. In the first chapter, we saw how we can extend the variation formulation of the Timoshenko beam element in order to account for weak Dirichlet boundary conditions, and we used the penalty and the Lagrange multipliers method in order to achieve that. In this chapter, we're going to concern ourselves with the so-called Hellinger-Reissner principle, and we will apply this principle in order to extend the variation formulation of the Timoshenko beam in order to account for the weak application of the kinematics. And let us elaborate on this. So in this slide, I have already gathered up all the underlying equations that we need for laying down the differential equation for the Timoshenko beam problem. So to the left, we see here a sketch which you should be already familiar with, where we have a beam which has a given set of material parameters, which are the shear correction factor, the shear modulus, the cross-sectional area, the Young's modulus, and the moment of inertia. This beam can be subject into external body forces, so to speak, which are distributed loads and distributed moments. Those are the Q bar and the M bar, as you can see here. Those can be applied all over the domain of the beam. Whereas there can be also a portion of the boundary, which we call the Dirichlet boundary, the essential boundary, where we can apply conditions on the primal unknowns of the problem. And please recall the primal unknowns of the problem are the vertical deflection indicated here, denoted by W, and the cross-sectional rotation beta. Whereas in another portion of the boundary, which we call gamma n, which is actually the natural boundary, we can apply conditions based on load. So basically applying loads on this corresponding boundary of the problem. And these loads can be in terms of vertical forces, Q bar in this case with capital, or bending moments, which are indicated here with the M bar. Okay, now the differential equation of the problem is laid on the right of the slide, where we can see firstly the equilibrium with respect to the vertical forces. The second equation accounts for the equilibrium with respect to the moment. And the equations afterwards are nothing else but the boundary conditions. So in this case, we actually have boundary conditions which are applied on the primal unknowns of the problem, the vertical deflections and the cross-sectional rotations, and boundary conditions applied on the Neumann boundary, which are basically boundary vertical forces and boundary moments. Okay, so to the lower left of the slide, we see now the kinematics equations that you should be already familiar with. They're indicated here with a yellow color, and we have the definition of the shear deformation, which is the derivative of the vertical deflection plus the cross-sectional rotation. And afterwards, we also have the definition of the change in the curvature, or curvature itself, if you will, which is nothing else but the derivative of the cross-sectional rotations. Moreover, we also have the constitutive equations, which are indicated here with a green color, and those are with respect to the connection of the reaction transverse shear forces and the shear deformation gamma, and the reaction bending moments M, and their connection to the change in the curvature or curvature itself, kappa. All right, what we've seen so far in the first chapter, where we talked about the Timoshenko beam formulation and its finite element discretization, we saw that we applied those subsidiary conditions, like the kinematics equations and the constitutive equations, strongly into the problem. How can we tell that was a strong imposition? Because we actually used the variational formulation at the time. We called it the principle of virtual work, and we simply went and substituted these equations directly into the weak form. By doing so, we impose these conditions strongly, which means that the solution doesn't have the flexibility not to fulfill these equations. And please recall now also that for thin beams, the big issue we had was the so-called transverse shear locking, which was stemming out of the Kirchhoff condition, which tells us that the gamma, so the shear deformation, has to be equal to 0 for thin beams. But in this case, due to the choice of basis functions which were linear for the two noted linear elements, there we can see that the sum of the derivative of the vertical deflection plus the cross-sectional rotation wasn't possible to be equal to 0. And that was amplified in the formulation itself, leading to extra spurious transverse shear forces, which were the reason why we have the shear locking in the first place. So now the idea that comes to us, and having already seen how to extend variational formulations based on variational principles, is to basically relax this condition in a sense, so not to apply it strongly point-wise as we did before, but rather take the kinematics equation, and now I'm referring to the first one here for the shear deformation, and try to apply that weakly into the problem, into our formulation. Then for this presentation, I'm gonna go ahead and proceed and apply both of the kinematics conditions weakly into the problem, but the issue that we have with the transverse shear locking obviously stems out of the first equation, which has to do with the transverse shear forces related actually to the shear deformation itself. Nevertheless, I would like to keep the presentation general, so I'm going to use the Hellinger-Reissner principle in order to apply both kinematics equations weakly into the formulation itself. However, the second set of equations here, which are the constitutive equations, those are going to be applied strongly into the problem, as we did it also in the original formulation of the Timoshenko beam problem. All right, and with this introduction, I would like to get started. So, in order to lay the Hellinger-Reissner principle, I'm going to write it here. This is a variational principle, obviously. The first thing we need to do is, as we did in the previous part of this chapter, take both of the equilibrium conditions, which are valid in the domain, multiply them with corresponding test functions, integrate over the whole domain, and then perform integration by parts. I mean, this is exactly what we do typically when we want to go from the differential equation level to the variational form itself. So from the strong form to the weak form, and this also holds backwards due to the variational principle that we saw in the previous part of the lecture of this chapter. So the first condition here tells us that Q of x plus Q derivative, it should be equal to 0. The second one tells us that m bar x plus m prime minus Q, it should be equal to 0. Okay, so the first one is the equilibrium with respect to the vertical forces, and the second one is the equilibrium with respect to the moments, the bending moments themselves. Now, what we want to do here is to multiply each of these equations with the test function, integrate over the domain, and perform integration by parts. Okay, what is the corresponding energetically conjugate test functions that we need to multiply each of the equations here on this slide? So the first one is actually residual of force, I would say, right? So in this case, in order to account for virtual work, we would need to multiply this equation with vertical deflections, which makes absolute sense because we talk about vertical forces. So in this case, that would be basically a Q, and I'm going to skip now the dependence on x, it's pretty obvious, plus Q prime, all multiplied with a delta W, because that's the variation of the vertical displacements. It should be equal to 0. And also we need to integrate over the domain, so 0 to L dx. Okay, now what about the second one? Similarly, this is going to be integral from 0 to L. Now the condition is m plus m prime minus Q. Multiplied now the variation of the cross-sectional rotations, which is the energetically conjugate primal unknown of the problem with respect to the moments. And so it performs actually work on the moments, and this has to be equal to 0. Okay, now we have these two conditions, and please recall, because these two test functions, the variation of the vertical deflection and the variation of the cross-sectional rotation, are independent variations from each other, so we can actually go ahead and sum up those two equations. And this will lead us into the following form. That's going to be basically integral from 0 to L, Q bar plus Q prime times delta W dx, plus integral from 0 to L, m plus m prime minus Q, all multiplied with delta beta, and here I forgot a dx. Dx should be equal to 0. Okay, so now we summed up both the equations. What is the next step? Obviously, the next step in our workflow here is to split the integral into the underlying parts. Then we're going to have the load terms, and this is going to be integral from 0 to L, Q bar times delta W dx plus integral 0 to L m bar times delta beta dx. And then we are proceeding with the other domain terms, which have to do with the internal work, so to say. And here what we have is plus integral from 0 to L, and we start with the shear part. That's going to be basically Q prime times delta W dx. And the second one I'm going to write in the next line, plus integral from 0 to L of m prime times delta beta dx minus integral from 0 to L Q times delta beta dx. And this has to be equal to 0. Okay, we arrived at this equation now. The next thing to do here is to perform integration by parts in the corresponding terms that have derivatives on the forces or in the moments. And let us go ahead and do that. I know these expressions are a little bit elaborate, but please follow along. Once again, we start with the boundary terms, just for the sake of having everything complete, 0 to L. And now we'd like to put the variations in front. That's also the workflow that we've seen in the previous part of the chapter. So it's going to be delta W times Q bar dx plus integral from 0 to L delta beta times m bar dx. And now I'm going to go ahead with the boundary terms first, because when we want to perform integration by parts, actually, this term here is going to give us some boundary terms. And the same thing will hold also for the second term. It's also going to give us some boundary terms. And these boundary terms are needed in order for us to be able to apply boundary conditions. And this is exactly what we said in the previous part of the chapter. And I hope that's clear up to this point. So doing here the integration by parts on the first term here, that's going to be basically the boundary term of delta W times Q, 0 to L. And this is actually nothing else but basically the evaluation of the integral on the boundaries, because we have a finite set of points here. So I just simplify the expression, obviously, minus the integral from 0 to L delta W prime times Q, because the derivative now has been shifted into the test function delta W, dx. And then we go with the next term, which is going to be plus delta beta M, again evaluated on the boundary, because we're talking about one-dimensional integrals here. We don't have to write integral over gamma d or something. The gamma d is clearly either the 0 or the L or both of them together, minus integral from 0 to L delta beta, now the derivative goes to delta beta in fact, times M dx. And please recall we had another term here, which was minus 0 to L delta beta without any prime here times Q dx. And this has to be equal to 0. Okay, now I would like to write down this equation once again. I'm just writing again the boundary terms. And for the sake of being rigorous, I'm writing the whole equation again so that I make sure that there is no inconsistency here. And what I want to do now is basically combine these two terms. So basically, I would like to combine this term here with this term here, because they both have the reaction transverse shear forces. So that's going to be basically nothing else but delta W times Q, 0 to L, plus delta beta times M from 0 to L. So I put the boundary terms together, and I reserve another line for me to write down the terms which are related to the internal work. And in this case, it's going to be minus integral from 0 to L. And now you will see delta W prime plus beta times Q dx, right? Because I just summed up the two terms and I factor out the common factor, which is the Q here, the reaction transverse shear forces, minus integral from 0 to L. And now I'm going to the bending part actually of the stiffness, which is, as you recall, delta beta prime times M and dx. And this all has to be equal to 0. Okay, now at this point, if you recall, we would go ahead and we would replace Q with the constitutive law, and then we would also apply the kinematics equations, and we would end up with a quadratic form of our variational principle, which we would go ahead afterwards and discretize with finite elements. Now, in the frame of the Hellinger-Reissner principle, we are not doing that. So in this case here, we don't apply strongly the kinematics. So we don't go ahead here and replace anything. So this term is going to be left like you see it on this slide, and the same about this term here. We're not going to set them equal on the one side to gamma and on the other side to kappa, because we want to apply this condition weakly in the frame of the principle Hellinger-Reissner. Okay, so I just would like to highlight this equation here because it's quite important, and maybe I also would like to write it in a closed form, because we've seen it also in the first chapter like this, so it doesn't matter. This is relatively straightforward. I have to write load terms. These are the load terms in the domain. And then I have also the boundary terms. And I hope by now you're already familiar with this notation here from 0 to L. And now I would like to put together all the terms that have to do with internal work, because it's going to be easier for us for the discretization phase. And so this is going to be integral from 0 to L. And let us put everything together now. So that's going to be a delta, right? And this is going to be a vector from this side. So this is going to be basically W prime plus beta, the one component of the vector, and the second component of the vector is beta prime. Okay, times basically the Q and the M and all this dx. Okay, so I brought these two terms together because this is going to help us a lot afterwards when we go for the discretization with the finite elements. And all this has to be equal to 0. So again, for summarizing, up to this point, we haven't applied neither the kinematics equation subsidiary condition nor the constitutive equations into the system strongly. So nothing has been applied yet. So the next thing we would like to do now is to identify what we want to solve for. Right, in this case, we know that our primal unknowns are, and I'm going to write it down, so the primal unknowns of the problem are the vertical deflection W, which is a function of the space, and the cross-section rotation beta, which is also a function of space. Okay, however, in this case, because we're not gonna replace the reaction forces with the constitutive equations and then also apply the kinematics equations to establish a direct relationship between the resultant stresses and the primal unknowns, we're gonna have new unknowns into the problem. And that's actually something which we could combine nicely with the previous part of the chapter, because there we also had extra unknowns. We call them Lagrange multipliers in the case of the Lagrange multipliers method. And those were related to forces and moments. This is going to be the exact same thing here. So these Q and M's that we see here, we're going to have to solve for them. So this we would like to call as secondary unknowns. And those are going to be basically the Q, which is also a function of X, is defined also within the domain of the beam, and the moment, the M of X. So we are having an extended variation formulation for which we try to solve for 4 in total fields. Now, I would like, for the sake of the presentation, and it is also mentioned like this in the lecture notes as well in the PDF handouts, I would like to group those both of these quantities into basically the primal unknowns. I would group them into a vector U, and this is going to be basically the Wx beta x, just to highlight that this is a function of space. And the next vector is going to be called beta. And now please try not to confuse yourselves. I'm sorry for this. I'm using the same notation as in the PDF handouts, but this beta is a vector. It doesn't have to do anything with the cross-sectional rotation here. It's just a vector that contains both of the transverse shear forces and the bending moments. So the vectors or the unknowns of the problem that I'm trying to solve for is the primal unknowns, the U, which is the vertical deflection and the cross-sectional rotations together. And the second set of unknown variables, the secondary variables in this case, which are the transverse shear forces and the bending moments. Okay, I hope that makes sense. As the next step now, I would like to look at this equation that we have above. So this is just one equation that we've written, and this equation actually is to be solved for 4 unknowns, right? In this case, it's going to be, again, the vertical deflection, cross-sectional rotation, reaction transverse shear forces, and reaction bending moments. Now, I would like to say at this point that this equation is not enough for us. I mean, we have more unknowns than equations. So we need to come up with another equation. And for this, I would like to motivate the discussion from what we've seen already in the part 2 of this chapter. If you recall, we actually need another set of equations that is purely associated with the variation of the Lagrange multipliers. So in this case, we would need another equation. And this equation in the part 1 of the lecture, that stemmed out of the boundary conditions. In this case, we're going to use the kinematics equations to obtain those terms. So we just have to recall now the kinematics equations, and we have that the shear deformation gamma is equal to the derivative of W plus beta. And this we can write it in a residual form now. So this is going to be gamma minus W prime minus beta here. It should be equal to 0. And the same holds for the second kinematics equation, which has to do with the change in the curvature, which is equal to the beta prime. And for this, we know that if we bring everything to the left side, we obtain the residual form of this equation as well. Okay, so we have these 2 residual equations. And now, as we already familiarized ourselves with how to use variational principles in order to obtain variation formulations from corresponding differential equations, we know that we have to multiply those 2 equations with some variations. Now let us think. The first equation here represents basically the kinematics with respect to the shear deformation. And please try to remember now what we had already seen in the first chapter. In this case, we would need to multiply the shear deformation with a variation of the shear forces in order to obtain work, and then integrate over the domain, of course. So the first equation, we're going to multiply the residual form of the kinematics equation related to the shear deformation with the variation of the transverse shear forces, and then integrate this over the domain 0L, and this is going to be equal to 0. Now we know from the principle of variational calculus that this equation here and that down here are one-to-one equivalent, which means that we can go from the one to the other, provided that the equation here that I just wrote, it is valid for all admissible variations of the shear forces. Now, we can play the same game, and you can imagine what happens in the second equation. So we need to take the second residual equation associated with the change in the curvature, kappa minus beta prime. And this we have to multiply now, obviously, if you recall from the first chapter where we learned about the Timoshenko beam formulation and the corresponding virtual work. In this case, it has to be multiplied with the variation of the moments and be integrated over the domain 0L dx, and this has to be equal to 0. Okay, I hope that makes sense up to this point. As we did previously, we can also go ahead now and we can sum them up, and we will obtain the following. So that's going to be equal to 0 to L gamma minus W prime minus beta times delta Q plus integral from 0 to L kappa minus beta prime times delta M dx is equal to 0. Okay, let us inspect this equation for a second. That's quite important. So here we have variations of so-called Lagrange multipliers in our case, which are nothing else but the reaction transverse shear forces Q and the reaction bending moments M. Okay, this is something that we didn't have in the previous equations. If you just look at it, we don't have any variation of the Lagrange multipliers, and that's something we need in order to obtain enough equations with respect to how many unknowns we have in order to be able to solve the problem. Okay, now obviously we can go ahead and take this equation and integrate it to the previous equation, so basically sum it up with that one, but I'm not going to do it at this point. I just want to motivate you that this equation is needed because we have to somehow obtain equations and terms which contain variations of the extra unknowns that we add into the problem. And those extra unknowns are in this case, again, the reaction transverse shear forces and the reaction bending moments. Okay, I hope that everything up to this point makes sense. Now we're going to go ahead and, as we said, we don't want to apply the kinematics equations strongly into the problem. They're going to be imposed weakly. And this is exactly what we can achieve with this equation here. Those are applied weakly so far. We haven't said that this term is equal to 0, right? Because if this term would be equal to 0, then we would apply this equation strongly. But this is not the case. So in this case, we apply the condition weakly. Now, the next thing we need to do is actually leverage the constitutive equations, which we haven't leveraged so far. Let me just write that also here for the sake of clarity. Okay, so we need to leverage somehow the constitutive equations. To do that, we are going to go ahead and perform the multiplications here in the integrals to obtain another expression of this form here, which is going to be equal to integral from 0 to L. And you see there is a few integrals that we have to evaluate always. That's going to be basically gamma times delta Q dx, and now minus integral from 0 to L, and I'm going to group the two terms together here, the derivative of the vertical deflection and the shear deformation. That's going to be W prime plus beta times delta Q dx. And now we go to the next part, which has to do basically with the moments. And this is equal to plus integral from 0 to L kappa times delta M dx minus integral from 0 to L. And this was beta prime times delta M dx. And this has to be equal to 0, of course, like we said previously. Okay. Now, the next thing we need to do here is, as we said, to apply the constitutive equations. So I'm going to go ahead here and apply the constitutive equations. Okay. And what will happen now is the following. I'm going to also bring the variations in front because this is a better notation in terms of how I would like to lay down the finite element equations later. So this is going to become integral from 0 to L delta Q times gamma. And now here is the point where I would like to apply the constitutive equations. So the gamma in this case is going to be nothing else but 1 divided by alpha G A, recall that, times Q. And you see I obtained here a symmetric term. Please recall that we always seek for such quadratic terms because they are good for the formulation itself. They don't change the nature of the formulation. If we have a positive definite system of equations, then these kind of terms don't really change this nature of the system. And so then we have the next term, which is going to be basically, and I'm going to go to the next line and use that term here first. So it's going to be plus integral from 0 to L delta M, applying once again now the constitutive equations with respect to the moments. So that's going to be 1 divided by EI times M, another quadratic term. And the next set of terms is the ones which have the minus in front, and this is going to be integral from 0 to L delta Q times W prime plus beta dx. And the last term is minus integral from 0 to L delta M times beta prime dx, and this is equal to 0. Okay, so here we have another set of equations which contain the unknowns that we seek for, and the variations of the Lagrange multipliers fields, which is necessary for us to obtain the needed amount of equations in order to be able to solve for all of the unknowns that we have into the problem. Okay, now in the next slide, I would like to write all these equations together to just get started, because after that, we're going to go ahead and discretize the terms. So please recall the equation we've seen previously, which was the long one here, that one. And I'm going to have to write it again. So integral from 0 to L delta W times Q plus integral from 0 to L delta beta times M bar dx plus the boundary term delta WQ 0 to L, the boundary term with respect to the moments delta beta times M, and then we have the internal work, which is basically this one here. And there was a minus in front, so this is important to recall. 0 to L, the vector, it was a virtual vector in this case, of W prime plus beta, and the next term was beta prime, and multiplied with the Lagrange multipliers, or the transverse shear forces and the moments, dx. And this has to be equal to 0. The next equation, the equation that we just laid down before, I'm going to also write it in a matrix form that will help us a lot with the finite element formulation. And I would like to start in this case first with the negative terms. So that's going to be minus integral from 0 to L. Let's group everything together in vectors. I would like to first group into vectors the variations of the Lagrange multipliers, basically the transverse shear forces and the bending moments. So this is going to be delta QM, the second term of the vector, and this has to be multiplied now with the W prime plus beta and beta prime dx. And now please note, associate these two terms, like we have this term here above and this term down here. I mean, the one is the symmetric term of the other one. That's great, actually, and this is what we strive for when we write variational formulations. We need to have such terms because this means that the equation system at the end is going to be symmetric, and this is something we really need. I mean, symmetric systems are one step forward to have a rigorous, let's say, proof that the final discrete equation system has a unique solution. So please recall, we need to have a symmetric system and also a positive definite system in order to be able to tell that the solution of the system is unique. If we don't have any of these conditions fulfilled, then we cannot tell in advance whether the system has a unique solution. So nevertheless, it's good to have a symmetric terms appearing to our problem, and this is exactly what is happening here. And the last term we need to add here is the positive term on the previous equation, which was the first part, and I would like to also group it into vectors. You see that is quite useful to be able to do these groupings. Quite helps a lot. So again, this associates purely the Lagrange multipliers and their variations. So this is going to be delta Q and M. Then there's going to be a matrix, which we see now how it's going to be called. That's going to be 1 divided by alpha GA 0, 0, 1 divided by EI. And this is actually the matrix called the compliance matrix. Compliance matrix, and which is actually the inverse of the material matrix, right? In this case, we have the compliance matrix. Okay, and this is going to be post-multiplied actually with the Lagrange multipliers themselves, actually the fields we seek for, dx, and this has to be equal to 0. Okay, this slide contains all the essence of the Hellinger-Reissner variation formulation for the Timoshenko beam problem. Please take a note on this, and just recall that we have two equation systems in this case, where we seek for 4 unknowns in contrast to what we had in the first chapter. We seek for both the primal unknowns, which are the vertical deflections and the cross-sectional rotations, along with the reaction transverse shear forces and the reaction bending moments. So in total, we have 4 fields that we seek for, and therefore we have to have a corresponding number of equations to be able to solve for. Now, I said 4 fields, and you would have expected maybe 4 equations. In this case, I do have 4 equations. It's just like that each of these 2 pairs of equations have been grouped together. So the first equation here groups 2 equations together, whereas the second one groups also 2 equations together. And this can be figured out or can be understood by the number of the variations we have, the independent variations. So we always have as many equations into the system as many are the corresponding independent variations. Okay, and at this point, I think we can go ahead and proceed with the finite element discretization, which we would need actually in order to be able to arrive into the final equation system that we want to solve for. And for this, I would like to start with the second equation first. So I'm going from the one down here. But first, let's talk about the discretization itself. So we said before that we had a field U, and this is equal to the W and the beta. Now, this is straightforward. We know that if we use a set of shape functions or basis functions, which we would call here n, that would be equal to n1, 0, 0, n1, up to n. And let us give a number here. It's going to be n1, I need to use another n afterwards. 0, 0, n of n1. And this is going to be multiplied with a vector, which is going to be basically, if you recall, that is w1, beta 1, w2, beta 2, and so on and so forth, up to wn1, beta n1. And we close the square brackets here. Okay, so how do we call this vector? This vector, we need to give it a name as well, and I'm going to give it a name as u vector hat, just to indicate that this is the discretized form of it. It's like the degrees of freedom, okay? Just differentiate this u underlined and hat with the previous u here, which accounts for the continuous fields. That's a discretization we do for the primal unknowns, and we will do also a discretization for the secondary unknowns, which we call beta underlined, because this is a vector as well. And please, once again, try to differentiate between this vector beta and this cross-section rotation beta. The one is a scalar, the other one is a vector, and I wanted to keep the same notation as in the PDF handouts. That's why you see this naming classing here, but I hope that it's clear, at least because the one is a vector. And this is the q's and the m's. And now we also can use some basis functions to discretize those fields, but we are not confined in using the same shape functions or basis functions as we used also for the primal unknowns. So we can use another set of shape functions, and this one I'm going to call n1 tilde, because it's another shape function. It can be, for example, a linear one, although we use the quadratic one for the primal unknowns, right? So it can be anything. In this case, n1 tilde, 0, 0, n1 tilde, up to n, and now we'll use n2 here, okay, tilde, because we can have another number of shape functions for the secondary unknowns as for the primal unknowns, 0, 0, n2 tilde. And this is going to be multiplied now with the vector as before, but this is not going to contain, of course, degrees of freedom that are associated with the vertical deflections and the cross-sectional rotations, but rather with the vertical transverse shear forces, Q1, and the moments themselves, the bending moments. So M1, so Q2, M2 for the second one, and so on and so forth, up to QN2 and MN2. And we close the square bracket here. And how we would call this vector here, this is going to be pretty straightforward as well. We will call this one here a beta underlined hat, because it's a set of degrees of freedom. All right, so I hope that that's clear up to this point. And now, using these notations, let's see what other constituent we would like to describe with respect to the degrees of freedom. And if we look at the equations before, we have here this term, this vector, which is the derivative of the vertical deflection plus the cross-sectional rotation, and the second component is the derivative of the cross-sectional rotation itself. So let's see how this term is being discretized. I mean, we've seen that already in the first chapter. There is nothing new here. It's just for the sake of laying the equations rigorously down. Again, that was w prime plus beta and beta prime. That vector here we try to discretize. This is going to be equal to, of course, you know that, n1 prime n1, 0 n1 prime, and the prime here holds for the derivative with respect to the physical space, please recall, but the basis functions are typically given in the parametric space. So to evaluate these derivatives, obviously we need to do a transformation based on the chain rule that you already know, and this is going to be carried over up to n1 prime, n1, 0, n1 prime. And this is obviously is going to be multiplied now with the degrees of freedom of the primal unknowns, which is going to be u hat underlined. Okay, so we discretize this term as well. And now I would like to give some names to these matrices. So this matrix here, I would like to call it the shape function matrix n. Okay, this down here, I'm going to call the shape function matrix tilde, which is associated with the secondary unknowns. So the n is associated with the discretization of the primal unknowns, and the n tilde matrix here is the shape function matrix associated with the discretization of the secondary unknowns. All right, now having all these constituents, we can also give a name to this one here, but I think that should be clear because this is the B operator matrix we had in the beginning of the lecture. So this is nothing else but the B operator matrix. When we discretize, if you recall, the strains for the Timoshenko beam and the Reissner beam plate later. Okay, now since we have now these three matrices, which are all the matrices we need to have, we don't need to have more than this, we can go ahead in the second equation that we laid before, that one here. And please let me give also a name to this compliance matrix. I'm going to call this one S with double underline because that's a matrix. Okay, and now to discretize this equation here, what do we have? That's going to be equal to, let's start with the discretization here. I'm going to write it as a title. Okay, so the first term is going to be equal to minus 0 to L. And because we have the first term here, delta Q and M, this is a transpose, obviously, of that term that we discretized before. This one, again, is the transpose of that one here with a variation. So this is going to be nothing else but delta beta vector hat transpose times n tilde transpose. Okay, so this term here is the discrete form, the discrete version, so to say, of, and I'm going to write it down here just for the sake of completeness, delta Q M. And I hope that's clear. And then we need to multiply that one here with this vector, which is, if you recall again, the strain vector we had seen already in the first chapter, and which is associated, of course, with the B operator matrix we just wrote up there. So that's going to be equal to times the B operator matrix. And this is actually, again, just for the sake of clarity, it discretizes the term W prime plus beta and beta prime times, of course, degrees of freedom. So that's going to be U and not beta, okay, dx. Okay, so that was the first part. And now for the second part, we talk about that one here. So this is a plus here. Okay, so this is going to be, and I hope I don't have any mistake, plus integral from 0 to L, delta beta underlined hat times n tilde transpose times the compliance matrix times n tilde without a transpose times beta, the unknowns that we are seeking for the secondary unknowns, dx, and all this has to be equal to 0. Okay, so we arrive at this equation here, and now I would like to go ahead and actually take out the degrees of freedom from the integrals because they don't need to live in the integrals. So this is going to be minus delta beta underlined hat transpose integral from 0 to L n tilde transpose times B operator matrix that we've seen before times dx times U plus delta beta hat integral from 0 to L n tilde transpose times S times n tilde dx times beta. And all this equal to 0. Okay, so that's a nice equation here. What we see is that all the equations is associated with a variation of the secondary variables. So basically the reaction transverse shear forces and the reaction bending moments. Therefore, we can actually go ahead and factor out the virtual degrees of freedom. So delta beta vector transpose all can be multiplied with minus integral from 0 to L and shape function matrix associated with the secondary unknowns transpose times B operator dx times U hat plus integral from 0 to L n tilde transpose times compliance matrix times n tilde transpose dx times beta is equal to 0. Okay, so that's actually the second set of equations that we need to complement the system with in order to be able to solve it actually. And now the most important thing is that, of course, we have the degrees of freedom we want to find, and those are the primal ones here and the secondary ones here. All right, now what about the associated matrices? The first one here, and I'm not going to use the minus in front, I can skip it here. I don't have to define my matrix with respect to this minus, so this is going to be purely this matrix. And this we will call here G. This is going to be called the G matrix. And this is to be basically compliant with whatever is written on the PDF handouts. And the second one here, this matrix, we're going to call it the H matrix. Okay, so if we skip the variations, of course, we can say for all variations, so we can skip the variations. And what we obtain? We obtain the following system. So we're going to have G times the vector of the primal unknowns, and the minus go to the G here, plus H times the degrees of freedom associated with the secondary unknowns equal to 0. Now, in order to be actually keeping the same notation as in the PDF handouts, I would like to multiply this equation with a minus. So we're going to obtain here basically minus H times beta plus G times u is equal to 0. Okay, so we obtain this equation here. Very nice. Now we need to find also the second set of equations to be able to solve for both of these fields. And you recall now that I started from the second equation down here for the discretization itself. I started from this one here. Now I would like to go to the one above. Let us talk briefly about the one above because it's also interesting. So we have the first line that is associated with the forces that are acting in the domain of the beam, which is the first two terms, and the second two terms, which are accounting for the boundary conditions themselves. So I won't expand on this because we already saw how to apply those. I mean, the first part is applied in the same manner, or is being computed in the same manner as the internal work. We just use Gauss points and we multiply it with the corresponding externally applied distributed moments and vertical forces. Whereas for the second part, we can either apply them strongly, the conditions themselves, meaning that we go and we remove rows and columns, or we can use the methods that we've seen in the first part of the chapter, meaning the penalty or the Lagrange multipliers method. So, and of course, with respect to the boundary loads, we know already how to apply them. I mean, we have to go to the corresponding entry of the load vector and just add a value, consider whether that's a moment or a vertical force, so to put it in the right place. So I'm not going to concern myself now or consume myself now with this equation up here, but I'm going to go straight ahead to the second line, which is the most important here, is the internal work. So if we start with the discretization again of that term, what we're going to have is the load vector. I'm going to call it F, and this is going to be pre-multiplied with delta U hat transpose. Okay, and this again, please recall, this is grouping all the terms that have to do with the load. I'm not going to show again how to derive the loads because we've seen that already in the first chapter. Now the second part, which is the important one here, and you see I have to go back quite a few slides, is this one. There is a minus in front, as you can see. And because there is a minus in front, I would like to, actually also change the signs here of this equation to be kept consistent with respect to what is written in the PDF handout. So I'm going to use the minus actually for the loads, and I'm not going to use the minuses for the internal work. I hope that's fine. So this is going to be basically here a minus, of course, makes sense, plus an integral from 0 to L. And again, we do the same exercise as before. Here, that's going to be basically delta U hat transpose, and this is going to be the B operator because that's transposed, of course, because this term is discretizing nothing else but the term delta W prime plus beta and beta prime. This is the term we are discretizing here, and of course that's, you can imagine that the transpose of that is a column vector times the Lagrange multipliers. So in this case, that's going to be basically the n tilde beta dx. Okay, and this has to be equal to 0. Now, if we go ahead and do the same exercise as we did for the previous equation, we can filter out all the virtual degrees of freedom that are associated with the primal unknowns, and that's going to be delta U underlined hat transpose minus F plus integral from 0 to L beta transpose n tilde dx, and the beta, the degrees of freedom associated with the Lagrange multipliers, can go out of the integral because it's constant, and that can be equal to 0. Okay, and now please recall that this term here, we've seen it before, and this is nothing else but the G we saw before transposed. Okay, we can go to the previous slide and you can see the G was the n tilde transpose times B, talking about this one here. Whereas in this case, the G, or this term, the G transpose, is the B operator transpose times n tilde. So it's actually literally the transpose of the previous term we saw. And how does this one here write now? It writes as follows. Once again, I can skip the variations because it holds for all the variations. Please recall that's one important principle of variational calculus in this case, because if an equation holds for all the variations, then we can actually skip the variations, right? This is what we also saw at the beginning with the integrals. So in this case, that's going to be equal to G transpose times beta. And all this has to be equal to F, right? Because I bring the F to the right-hand side. So I bring basically the F to the right-hand side of the equation. And so let's see the equations that we have now. We have two equations. The first one is going to be the one I wrote in the previous slide. So it's going to be minus H times beta hat, because it's the degrees of freedom, plus G times U. That's equal to 0. And the second equation is basically G transpose times beta equals to F. Okay, so we see now these two equations. I would like you to concentrate on this set of equations here. And as you can see, the second equation is decoupled with respect to the primal unknowns. It has only the degrees of freedom associated with the Lagrange multipliers themselves. And so now we can actually go ahead and write that in a matrix form. So we take equations that are already written in matrix form and we formulate bigger matrices out of this. By the way, these kind of operations are optimal to be programmed in Matlab because Matlab is designed to deal with matrices and group matrices together. So by doing that now, we have a system minus H, G, G transpose, and a block of zeros here times beta, degrees of freedom, and U degrees of freedom. The first line has to be equal to 0, and the second one equal to F. By the way, in the PDF handouts, the F here is indicated as R, and I just want to make sure that there is no confusion. I just want to keep consistent with respect to what I saw in the previous lectures. In the PDF handouts, this is written as an R, but throughout the lecture, we saw this load vector indicated as F. So I want to be consistent with respect to what we saw in the previous lectures as well. Okay, up to this point, everything is all right. So we can actually go ahead and compute these matrices and solve the equation system. Hopefully, this equation system is going to be determinate, which means that it has a unique solution. But of course, as we also saw in the application of the Lagrange multipliers method for the weak Dirichlet boundary conditions, this is not always the case that we will have a unique solution to the system, because with the Lagrange multipliers method, we are changing the nature of the system. The system is no longer coercive, it's called, or positively finite, which means that the discrete equation system may have also negative eigenvalues. And if this is the case, then we cannot be sure that there is going to be a unique solution to the system. And that's the exact same thing here as well. I mean, there is no difference. We are also using Lagrange multipliers for the weak application of the kinematics equations in the system. So the system is also here not positively finite. How can we tell that the system is not positively finite only by looking at this equation system? Is this zero block here? We have zeros in the diagonal. It doesn't matter where we have them, but we have zeros in the diagonal, and this is already an indication that the system is not positively finite. It may have also negative eigenvalues. Please note that this doesn't mean that the system will not have eventually a solution. It means that we cannot prove in advance that the system will have a unique solution. That's the sense here. All right. Now, what we can do here is actually eliminate the Lagrange multipliers degrees of freedom. And that's a trick which we call static condensation, which is actually the elimination of the Lagrange multipliers degrees of freedom, DOFs, from the equation system. Now, to do this, obviously we have to go to the first equation we had before and solve this equation with respect to betas. So in this case, we're going to have something like, let's just write the equation again for the sake of clarity. So this is going to be minus h times beta underlined h plus g times u is equal to 0. So here we can go ahead and say that the beta is equal to inverse of h times g times u. Okay, we keep this equation in mind, and we go ahead and we substitute that into the second equation here, the one down here. And there we obtain the following. I'm going to change slides. So we had G transpose times beta vector is equal to F. And by substituting the condition we had before, which was beta degrees of freedom is equal to H transpose H inverse matrix times G times U, degrees of freedom for the primal unknowns. And now we obtain G transpose times H to the power of minus 1, so inverse times G times U degrees of freedom is equal to F. And now here, please note that we have an equation system that looks exactly like K times U is equal to F, right? It's the same thing. But in this case, the K is a little bit more elaborate. So that is the K here that we have, the system matrix, so to say. And you see that in order to obtain this system matrix, we need to invert another submatrix of the initial system of equations we had. And so in this case, of course, the system is a little bit more elaborate from what we've seen already in the first chapter, in the classic variational formulation of the Timoshenko beam problem. So of course, we're going to have a little bit more elaborate computations in this case. But nevertheless, that's exactly the linear equation system that is associated with the Hellinger-Reissner formulation of the Timoshenko beam problem in this case. And important is to note again that what have we done actually? Why did we even go ahead and derive these equations? The initial thought we had is that we wanted to apply the condition with respect to the shear deformation, the gamma, which is equal to the W prime plus beta, weakly into our system, aiming basically that the resulting system of equations is not going to suffer from shear locking, right? Because here we applied this equation weakly. Okay. And of course, I would like to also motivate you, because in the lecture notes, you're going to see also another method which is called the Hubashitsu. And this method, for that method at least, similar to the Hellinger-Reissner, it is also applied weakly the constitutive equations, not only the kinematic equations that we've seen in this part of the chapter, which we applied weakly here, but there in the Hubashitsu method is applied weakly also the constitutive equations. So we have another set of Lagrange multipliers which are associated directly with the weak application or the weak enforcement of the constitutive equations. And I'm not going to lay down the equations for that. You can find everything on the PDF handout. We are concentrated here, at least for the chapter itself, and what I would like to show you in Matlab for the Hellinger-Reissner formulation of the Timoshenko beam problem and how this can be used to alleviate locking. And having said that, I would like to go ahead and show you the Matlab code which implements exactly this Hellinger-Reissner formulation of the Timoshenko beam problem. In the beginning of the live script to the left, you see what you've seen already so far in the previous live scripts that we used for numerical modeling of the system. In this case, important is to note that the equation that represents the Hellinger-Reissner formulation is down here. And as you see already, the constituents that contain the Lagrange multipliers, for example, and their variations, and so on and so forth, and the load terms, which are on the right side here, and they contain both source loads, which means like loads that are applied in the domain itself, and boundary loads. Okay, so let us take a look at the script. Firstly, we would like to see how the basis functions are defined. So we have, of course, the linear shape functions, and we also can visualize them and see what they are. You've seen that already in the first chapter, and the quadratic ones. So these are the functions we are going to use, along with some constant ones, but I don't have to plot the constant ones, you can imagine. For the constant discretization, we have only one shape function per element, and this is equal to 1. Okay, the next thing we're going to do is also, firstly, to choose a discretization for the Lagrange multipliers, which are the, in this case, the reaction transverse shear forces and the reaction bending moments. And we can use actually different discretization rules for both of these Lagrange multipliers, but in this case I would like to keep it uniform, and we can choose a discretization in this case that is either constant with a 0, 1 for linear, or 2 for quadratic. So we have these two options. And let's start with the constant ones, the 0, so I can run this section of the script and obtain the discretization that I'm going to use later for the Lagrange multipliers fields, which is again the transverse shear forces and the bending moments. Then we define the parameters of the problem. Here, please note that we have a relatively slender beam. We see we have the height is 0.01, whereas the width in this case it is 0.1, so it's a relatively slender beam. We would expect to have some shear locking in the case of the linear two-noded elements, and we will see that in a while. First, we create a mesh which is associated with the two-noded linear elements. So you see each element here has 2 nodes. Then we create also a mesh with a quadratic 3-noded element. And we see here, once again, for each element we have 3 nodes, as to be expected. We also apply the boundary conditions strongly in this case. I mean, for the weak application of the boundary conditions, I would like to refer you to the previous part of the chapter. We don't have to consider that again, but of course we can group everything together if this is desirable. Okay, the next thing is to compute the stiffness matrix associated with the two-noded linear elements. I mean, this is the sparsity pattern, and this is something that you would have expected already, and you have already seen in the first chapter. We can also see the sparsity pattern for the quadratic 3-noded elements. And of course, again, this is something you've seen already before. And of course, the sparsity pattern here for the quadratic elements looks different than the one for the linear elements because of the way that we are sorting the nodes per element. So each element sorts the nodes in a particular way. And lastly, we would also like now to compute the global matrices for the Hellinger-Reissner formulation. And in this case, we can also choose discretization for the primal unknowns, which are the vertical deflections and the cross-sectional rotations. And again, we use the same interpolation for both of these fields, right? For both the vertical deflection and the cross-sectional rotation. And we can choose in this case between 2 values only, actually. So either linear or quadratic. Nevertheless, in general, of course, you can have also higher order shape functions, but in the frame of this course, we've seen up to quadratic functions. Of course, you can go beyond that. Using the Lagrange polynomials, you can go to any degree is desirable. In this case, I'm going to use linear functions for the discretization of the primal field, so linear basis functions. So recall, please, that for the discretization of the Lagrange multipliers, we used constant functions, and for the discretization of the primal fields, the vertical deflection and the cross-sectional rotation, we use linear ones. So we have a constant linear interpolation here. It's not an equal ordered interpolation for the Lagrange multipliers and the primal unknowns, but rather a constant linear interpolation. All right. Now we see the sparsity pattern here looks very similar to what we have in the linear two-noded elements, which is quite good actually because we have less degrees of freedom. It's linear elements again, two-noded linear elements. And in this case, it is already containing the information about the Lagrange multipliers, which have been condensed out with this inverse of the H matrix. And now we can go ahead and solve the system for each of these three different setups. So the first setup, please recall, it has to do with the linear two-noded elements. And this we expect to have some locking, because we don't apply any selective reduced integration. So here we see the deflection that is in the millimeter range. We can already be skeptical here because the deformation is quite small. Now we can go ahead and use the quadratic ones, the three-noded quadratic ones, and see the deflection. We see now that we have actually around half a meter deflection, which already tells us that, okay, the linear ones are locking. I mean, it's pretty clear. We get a deformation in the range of millimeters, and for the quadratic ones, we get a deformation in the range of a half a meter almost. So it's basically 40 centimeters. And now we go to the Hellinger-Reissner discrete formulation and see how this system performs. Please remember that here we're using the linear two-noded elements, but we also included the Lagrange multipliers, which we actually afterwards condensed out using the methods we saw in the slides. And by actually doing that here to solve the system, we see that the system doesn't exhibit any locking. So we have the same deformation pattern that we had before with the three-noded quadratic elements, which is great. This is what we were looking for. So we have actually a linear two-noded mesh that is not locking without using selective reduced integration. Nevertheless, in this case, we are, of course, having Lagrange multipliers so that we are condensing out of the system. So if you see in this case here, it took a little bit longer to assemble the stiffness matrix. I would like to actually highlight that. If we go back and try to compute the stiffness matrix for the quadratic elements here, you can see that it's being done extremely quick. So that's just like in the blink of an eye. Here we have the stiffness matrix associated with the three-noded quadratic elements. But if we go now and we compute the same for the global stiffness matrix that is associated with the Hellinger-Reissner formulation, you will see that this will take a little bit longer. You see here Matlab is loading up on the left. So it's still running and running because we have to invert a matrix at each element. So it takes considerably longer time to compute this matrix for the Hellinger-Reissner formulation. So it is, of course, a formulation that doesn't lock, doesn't exhibit any locking, which is great. This is what we're looking for. But you see, it comes in a price that we have a system that is slower to assemble. And we also have a system that is subject to the Lagrange multipliers discretization, which can also cause troubles because the system, it is not positively finite in that sense. All right, so that was all that I would like to talk to you about with respect to the second part of the chapter, variational formulation of finite elements. And see you in the next chapter. Thank you very much for watching.